Hey everybody, welcome to Master the NEC, where we talk about the National Electrical Code. This is part 2 in a series on transformers, where we're going to today discuss how to size the overcurrent protection for the primary and the secondary windings of a transformer. Now this is pretty important because that protection ensures that that transformer doesn't break down, and there's certain rules in the code that we have to follow in order to size it. And so typically we're going to go to Article 450 of the National Electrical Code, and inside of Article 450 there's a specific section that deals with overcurrent protection, and that overcurrent protection is going to be what we use to protect the primary or the secondary of a transformer. So we're going to use these tables and how they correlate to what we're doing. Now, before we even get into that, we need to do a recap, because if you watched part 1 of this series, you see that we were dealing with a 75 kVA transformer code. So we're going to lay down the land, write these things down, because we're going to need it in our today's episode as well. So we have a 75 kVA transformer. It was a 480 volt primary and a 208/120 secondary. We already calculated following the formula that was in the part 1 of the series, where we determined that the primary rated current of that transformer was 90 amps and the secondary rating of that transformer, a current rating, was 208 amps. And again, that was very simple. Primary, we simply took the VA, which is 75,000. We divided in 831, which is our shortcut. Go back and watch part 1 of the video to understand that shortcut. And that resulted in 90 amperes. Okay, we ended up dropping off the decimal points and keeping 90. When it comes to the secondary, it was just that simple. It was 70,000 kVA divided by 360. Again, that was our shortcut, which is basically the voltage times the square root of 3. But we learned these shortcuts, and so it's 360. So when we did that, it equaled 208.33 amps, and we got rid of the 0.33 because we're going to work with 208. So that was our primary current, and that's our secondary current. That's the maximum output that we have of this transformer based on this 75 kVA transformer. Okay, so kind of that lays the land, so you now know where we're going when we start pointing out little things in this series. Okay. All right, so let's look at the graphic and see what we're talking about a little bit. So here's the graphic. And in the graphic, we're going to talk about how to size this right here. This is the primary overcurrent protection that protects the primary side of this transformer. And of course, right here is the secondary protection for this transformer. Now, there are some occasions where the primary protection can also protect the secondary of a transformer. Okay, and that is a unique situation, and we'll kind of look at that as we get at it. But for all intents and purposes, for the most part, you're going to have some type of primary and secondary protection. Okay, so we'll look at it when that rule allows you to not have to have secondary protection. Okay, for the most part. All right. So let's kind of dig into that. So let's go on and jump into the code, because we want to go on and get started into that. So here we are. We're at 450.3 overcurrent protection. Now, this overcurrent protection is for the transformer. It is not for the conductors. Now, ultimately, it might serve both needs, but right now, we're only trying to offer protection for the transformer. That's it. That's what we're trying to do here. Now, there is an informational note that reminds you that 240.4, 240.21, all of those things have to do with conductors. And so we have to remember that those conductors have to be protected at their ampacity unless some kind of tap rule applies or secondary conductor rule applies, and then we will apply it. Other than that, we have to remember that this protection that we're talking about here in 450.3 is simply to protect the transformer. That's all we're doing here. Okay, so we're going to keep it light and simple as we build on this knowledge. All right, so when we're back in the code, we're going to see that it deals with 450.3a, b, and c. Now, what is a and b? Because they're the two that we're going to deal with today. All right, what is a? A deals with transformers over 1,000 volts, and B deals with transformers 1,000 volts or less. Now, our transformer is a 75 kVA, 480 volt primary, 208/120 secondary. So obviously it doesn't exceed 1,000 volts. So it's 1,000 volts or less. So we're clearly going to be doing our overcurrent protection calculations based on table 450.3b. But there is a table 450.3a that deals with transformers over 1,000 volts. So you want to keep that in mind. Okay. And of course, we do have C, which we're not really going to talk about, which is dealing with voltage potential transformers, and that is voltage potential transformers installed indoors or enclosed shall be protected with primary fuses. So if that's the kind of transformer that you're dealing with, a voltage potential transformer, then remember that it has to be protected on the primary side with fuses. Okay. All right. So just remember that. But what we're going to deal with today is obviously we're going to deal with B. But while we're at it, let's go on and look at A. So A table is, again, transformers that are over 1,000 volts. And these percentages that are found in this table are percentages of the transformer rated current. And if you remember earlier, that transformer rated current is exactly what we calculated in part 1 of this series. That is where we took the VA and divided it by 831 for 480, or the VA divided by 360 for 208, or even if it was a 240, we can do the VA, which is 75,000 in our case, divided by 415 if it was 240 volt secondary lines. So that's the concept, and that's what our primary current rating is, and that's why it was important to follow part 1, because you have to build on those basics. Okay, so now we're moving on. We're getting more advanced. We're making sure that we size that overcurrent protection device properly. So let's go look at the code a little more and see where we're at. So now, if you were having to deal with transformers over 1,000 volts, then you would be in 450.3a. Of course, in our example today, we are not. But here it kind of gives you a layout of this table. And it's no different from this table down here. There's going to be 2 columns, and there's going to be 2 vertical columns and 2 horizontal columns that you got to deal with. But in here, you've got a primary protection column, and you have a secondary protection column. And again, both of this dealing with the primary is going to be over 1,000 volts, but in the secondary protection column, you have over 1,000 volts, and then you have 1,000 volts or less. So you could have an over 1,000 volts transformer where it has a primary coming in that's dealing with an over 1,000 volt application, but this secondary side is going to be in something that's 1,000 volts or less. So that's why we have this broken down like this here. Now, any location, what does that mean? That means a transformer that is located in any location. All right, wherever that transformer and that overcurrent protection is located, it doesn't really matter. So if that's the case, then you're going to follow this rule. Now, if you have supervised only locations, then you're going to follow the bottom portion of this. Okay, so any locations is a broad general application, and then supervised only locations allow you to move down into the second part of the vertical separation. All right, so let's go down and look at the code and try to, if we can understand what we're dealing with. So dealing with the location limitations for this overcurrent protection and the transformer application, it says any location. All right, where the transformer is rated not more than 6% of impedance, then the primary protection can be up to 600% of the primary transformer rated current. If it's a fuse that's being used for that primary protection, it can be up to 300%. Now, when it comes over to the secondary, and kind of to give you the layout of land, even though the transformer that we're dealing with is not over 1,000 volts, just to kind of give you an understanding, then this is your primary, this is your secondary protection. Okay, just to kind of give you the gist of where we're at. All right, so now the secondary protection. If it was over 1,000 volts that you're dealing with here, I don't know why that's doing that, over 1,000 volts. If it's a circuit breaker, then it can be up to 300%. Of course, we have a note 1 we'll talk about in a second. If it's fused, protected from the secondary of that winding, then you're going to have 250%. Okay. Now, what happens if that secondary protection comes out and it's dealing with something, let's say that transformer steps it down and it's going to be 1,000 volts or less. That's on that secondary, okay, depending on the turns ratio or whatever the windings are or whatever we're dealing with, then the circuit breaker or fuse protection for that secondary can't be over 125%. Okay, these are the basic rules. Now, if it is the impedance of that transformer, and again, that's going to be on the nameplate of the transformer or whatever you order. If the impedance is more than 6, but it is not more than 10, then you have these percentages that you can use. Okay, so primary protection not to exceed 400%. Secondary, the primary protection if a fuse is used not to exceed 300%. On the secondary side, protection of that transformer, not to exceed 250 if it's a circuit breaker, and not to exceed 225% if it's a fuse. And of course, again, if it results in a secondary that's 1,000 volts or less, then the circuit or fuse is not to exceed 125%. Okay. All right, and we have a bunch of different notes here that you want to deal with, but we're going to talk about the ones that are going to be more important to you. In this application is Note 1. Now, what is Note 1 saying here? Note 1 is saying, look, and we'll highlight this so that it's easier to understand and read it. Now, these are the maximum percentages, again, because that's what we're dealing with here. We're dealing with maximum values. But can we exceed this maximum? Well, basically, this is like an excise up rule. It says where the required fuse rating or circuit breaker setting, okay, which is based on this percentage, does not correspond to the standard rating, and that's in 240.6a. That's where you're going to see the standard ratings of circuit breakers or fuses. If it doesn't correspond, then a higher rating or setting that does not exceed the following shall be permitted. So this is our little next size up rule. A, it says the next size up or the next higher standard rating or setting for fuse or circuit breaker rated 1,000 volts or below. So again, if it doesn't correspond when you go to this value, so in other words, you take your primary rated current, let's do it right here. We take our primary rated current, which in our case, let's say was 90 amps, because that's what it was theoretically when we did our calculation for the 75 kVA, even though the transformer that we're dealing with is obviously not over 1,000 volts, but we're going to kind of use that to give us the example. So we're able to take the 90 amperes, all right, and we're actually able to do that times, in this case, let's say the impedance is not more than 6%, so primary protection is 600%. So we can take our 90 times 600%, and that is 540. So if we were to do that, and that doesn't correspond, and we were to go to 240.6a, and let's do that real quick, because we can get there pretty quickly. And we notice that 540 doesn't correspond here. This is 500, and then it jumps to 600. So we can actually do 600 and still be fine. Okay, so that's what it's talking about. All right, so just that's the general rule. We won't look at every one of them, but you get the gist of what we're talking about under that scenario. All right, now let me go back to 450 so that we can kind of finish what we're talking about here. Okay, so that's what it means here. Now, what about the B? Now, B says, well, the next higher commercially available rating setting for a fuse or circuit breaker above 1,000 volts. So what does that really mean? Well, the standard ratings are what's put in the table 240.6a of the NEC, but a lot of the manufacturers will make specific commercially available step sizes of circuit breakers. And so you would go to the next available one, okay? And that's how that would apply there, all right? So you would go to the next size, whatever commercially available one is from that manufacturer, the next size up from whatever your calculation is of the percentage. If it doesn't correspond, then you go up to the next size, okay? And that's for the over 1,000 volt applications, okay? So that's just what you do. So you're not going to use the standard ratings that are in 240.6a when you're dealing with the over 1,000 and you're using this rule, note 1. You're going to go to the manufacturer and find out, okay, well, that was 540. What is the next standard commercially available? Okay, I don't know. It might be a 550 available. Well, that's what you would go to, okay? So that's kind of how you apply that rule. All right, so, and again, that's how the note 1 applies to all of these and dealing with that there. All right, so let's go on and move down to the supervised only location. Well, what if I have a supervised only location? Then, of course, you can look at note 3. And note 3 says, gives us some definitions here. It says a supervised location is a location where conditions of maintenance and supervision ensure that only qualified persons monitor and service the transformer installation. All right, so what does that mean? Well, that means that maybe it's a big facility where the transformers and everything is locked behind an enclosure, a fencing, and normal people can't get to it. But people that need to get to it for supervision and maintenance and things like that and servicing, they are the qualified person. So if that's the case, then this is a supervised location only. And if that's what's your installation, what you're dealing with this transformer, then, and that's the case, then you can utilize the supervised location only rule. And so let's look at that and see how that applies. All right, now, again, regardless of the impedance values in a supervised only location, you're going to follow this column here. And if it's a supervised only location and you got a transformer rated impedance at really any rating of whatever that transformer may be, the primary protection would be at 300%, and the secondary, the primary protection for fuses would be at 250%. Of course, note 1 still applies here for that theoretical neck size up rule. But then over here, your secondary protection is not required. It doesn't mean that you might not choose to do it, but it's not required to do that. So, now, what if the impedance is not more than 6%? Then I can go up to 600%. And because I can go up to 600%, now we're going to get some requirements here to have some secondary protection. Okay, so that's for the circuit breaker. And I could go up to 250% for a fuse on the primary protection of that transformer. Okay, now notice that note 1 is not written here. Okay, so it's not referencing anything. This is the maximum. You can go up to the maximum of 600% here. Okay, obviously you could be less than that, but this is the maximum value to go to. Okay, so there's no need to remind us about any potential notes here. That is your maximum. Over here, we have the secondary. Again, you have 300%. You have 250%, which is your maximum that you could go up to. So it could be theoretically any amount less than that, from 100% up to. But here we're giving you the maximums again, because this is a maximum table. And of course, if the secondary conductors end up being derived and it's going to be 1,000 volts or less on that secondary of the transformer, then we'll go up to 250%. All right. Now, if it is more than 6% impedance, but not more than 10%, then you got 400% maximum for a circuit breaker, 300% maximum for a fuse, and of course, again, you have 250% for a circuit breaker for if it's over 1,000 volts for the secondary, and if it's a fuse, 225, and of course, it's 250 if it's 1,000 volts or less and it's a circuit breaker or fuse. Now we see a note 5 here, so you'll also note right here a 5. And what does this say? It says, a transformer equipped with a coordinated thermal overload protection by the manufacturer, okay, so that comes with it, okay, shall be permitted to have separate secondary protection omitted. Okay, so that's just saying that, you know what, I can also not have to have this secondary protection, provided that the manufacturer does provide me a coordinated thermal overload protection and it's incorporated in. So you would order it that way. If it's not in there, then here are the percentages that you use, okay? All right, so that's pretty much how that works. Now, let's go on and get to the one that we're going to deal with. So here's ours. And we'll go back real quick to our graphic because we want to lay the land again so we can kind of give you an understanding of where we're at. So we're back at our PowerPoint. And here's what we're sizing. Primary. We'll do this one first. All right, and we already know that we're going to size. Now, what if we were sizing this for an exam, and we're not going to deal with conductors in this episode. We're going to show that later. But what if we were sizing this based on 450.3b? And we already know what the primary current rating is. That was 90 amperes for our application, okay? 90 amps. So now let's go back to the code and see what it says. What is the maximum overcurrent protection that we would have here? Okay, so let's go to the code. All right, the maximum in our case is 250%. Now, why are we in this column here? Why are we in this horizontal column instead of this one? Because this is primary only protection, okay? And I'll give you an example in a second about when you can have primary only protection when you're dealing with transformers at 1,000 volts or less. But in our case, we're in the primary and secondary protection because if you go back at our graphic, you'll see that typically here that a panel board is required to have its protection. And so this has an overcurrent device in it protecting the panel board. Now it could actually be right here at the secondary source point where the voltage is derived here from the secondary. But typically it's not. It is you have, if it was right here, then you size everything downstream based on whatever the load is. But in this case, since we have no overcurrent protection here at the actual source of these secondary conductors, where they're derived here, then we're using maybe a 10-foot rule or even a 25-foot rule to size these conductors, okay? And then the overcurrent protection is right here. And those rules in 240.21, tap rules and secondary conductor rules, are afforded us because there is no overcurrent protection right here. But if I did put it right here, then I could simply size the conductors that are coming out of it, feeders, based on whatever the load was that it's going to be on those feeders, okay? So those conductors would be sized under the normal rules of Article 215 of the National Electrical Code, okay? 125% of the continuous, 100% of the non-continuous, and all those rules. Again, if you want to learn how to size conductors based on ambience, adjustments, corrections, loads, conditions of use, I encourage you to go to our video on our website or go to our YouTube channel and look for our D-rating demystified. And we talk about all the nuances of sizing conductors, okay? So this episode, we're really sizing the overcurrent protection, but if you want to learn how to size all those things, we're going to cover all that in here. But if you want to know all those nuances just generally, go watch that video. It's a great video. All right, so let's go back to the code. All right, so the code says that the primary protection here, right there, and we'll highlight that, make it easy to remember, is going to be not more than 250%. That's a maximum rating. So it's not going to exceed 250%. Okay? Now, here, and again, you've got it broken down into 3 columns here. So currents of 9 amperes or more. Then we have currents less than 9 amperes. And they have currents less than 2 amperes. For most of the exams we deal with, guys, it's going to be in this one right here. Okay, currents of 9 amperes or more. That's where we're going to be. And since we have a primary and secondary protection, and we haven't really talked about primary only protection in our graphic, then we would highlight 250%. And over here, we're going to highlight the 125%. And again, over here, we're also dealing with currents of 9 amperes or more. So this is kind of how I would highlight it if I was highlighting it in my code book, because these are the most important aspects that we're going to deal with, okay, when sizing the overcurrent protection for a transformer. All right, so let's kind of do that. So what is the maximum rated overcurrent protection device for a 1,000 volts or less transformer? What is the maximum? So if you're doing a calculation on an exam, we see that it's 250%. So if you got your calculator handy, you're going to actually do that calculation and see. All right, so we already calculated out in part 1 of this series what the primary current rating was, and that was 90 amperes. So we did 90 times 250%, and that equals 225. And so 225 is the maximum primary overcurrent protection. Okay, so if you had an exam question and it wanted to know what the maximum was, that was the maximum, and that's how you calculate, and that's what that 250% is dealing with there. Okay. Now we're going to look at an example why you typically would use a 250%, because under normal conditions, you really wouldn't do that. Okay. We typically are going to use 125% because depending on what we've got for these conductor protection and whether or not they're continuous loads or not, then we want to also utilize this primary protection to also protect the conductors. And of course, in 240.4, we need to protect conductors at their ampacity. And we have no allowance in 240.4 to do things like we do in motors or HVAC systems in Article 440, or like motors in 430, whereas we have a short circuit ground fault protection, for example, that can be rather large, but then the motors conductors that are feeding it, branch conductors or whatnot, can actually be much smaller, so they don't have the same ampacity as the breaker that it's terminating into or the fuse it's terminating to. And we get there because of the allowances in 240.4G. Okay, and so since it's not listed there, we're not afforded that same luxury. Okay, so in our case, we're going to make sure that we're also protecting those conductors as well. Now, if I did it at 250%, and we know that the potential output, I shouldn't say output, the primary current of that transformer is only 90 amps. And so if we chose a conductor that can handle 90 amps, in other words, we didn't add the 125%, maybe it's no continuous loads on this transformer. Whatever. So if we size those conductors at the 90 amps, which is the primary current, then I couldn't terminate that on a 225 amp rated overcurrent device because that wouldn't be protecting it at its ampacity. that would be a problem. So typically what we do is we'll assume a continuous load if we don't know otherwise. And I'm just giving you technical practices. I told you what you might get on an exam, but in realistic world, we would do this at 125%, and that'd be our suggested value. So let's redo that. So if I did that in the primary protection, I did it at 100. So it's 90, which is our primary current. And I did that times 1.25. Or 125%. That's 112.5 amperes. Now, if I take that and we're sizing the device, if I go look at 240.6a, I'll notice that I don't have a device that's rated for 112.5. It goes from 110 all the way up to 125. So since it doesn't correspond, I'm going to go on and use the 125. Now remember, it's not really a matter of using note 1 here. The fact is that overcurrent protection could go all the way up to as high as 250%. But since I don't have 112.5 rated device in the standard ratings in 240.6a, then I'm going to select 125. Okay, so I'm going to write that down. So it's 125 amp primary protection in this device. Now, what are we talking about? So if we look here, we're talking about right here. So this is 125. Okay. Now, incidentally, if I were to take these conductors at the 90 amperes, if that's what their current rating, and assume them at a continuous load, and size them at 125% of the continuous load, then I would take, and plus they are terminating in this the overcurrent device. Okay, so it corresponds with all of those rules in 215.3. So let's do this. So let's take the 90 times 1.25 again, and that's 112.5. So if I size a conductor that can happen to have, and of course we haven't done conductor sizing and that wasn't part of this video, but I'm just trying to show you what we're talking about here. If I size these at 112.5 amperes, let's see if that is okay for it to terminate onto a 125 amp overcurrent protective device. So that takes us back to the code. So let's go on and look at the code real quick because we want to go on and do this. I said I wasn't going to do conductor sizing, but we want to do it. So let's go on and go to 310.15b16. And that's conductor sizing. And we're not going to consider anything like adjustment and corrections, ambient temperature other than the 86 degrees Fahrenheit, 30 degrees Celsius. And of course, we're on the primary side, so we're not going to have more than 3 current carrying conductors in our application here for our example. If you did have anything that was other than the base values of this table, then you're going to have to do adjustment and corrections in accordance with 310.15 B2A for the ambient adjustments or the ambient temperature issue, or the number of current carrying conductors, that is 310.15b3a. So just remember, if you haven't watched our video on adjustment and corrections, derating demystified, go back and watch it. All right, so I need a conductor that's at least going to give me 112.5 amps. Well, it looks to me, and we're always going to assume copper, guys, unless we state otherwise. So here it looks like I'm going to be 115 amps. That's a 2 gauge. So I'm going to write that down, 2 AWG. And again, always assume copper unless expressed otherwise. Also, we're in the 75 degree column, and I didn't tell you that, so I should probably clarify. The reason we're in the 75 degree column, let's say our conductors are THHN, THWN-2. Now, that's a 90 degree rated insulation. But due to terminal limitations that are based on 110.14c, because these conductors are rated at 90, and because I have terminals that are rated at 75, because it's less than 100 amperes, I typically would be in the 60 degree ampacity column. But since my conductor has a higher ampacity value rating or temperature rating, I'm okay there. And because my terminals are 75, I'm okay there. So the limiting factor here is the terminals. So that's why we're staying in the 75 degree column here for our ampacity selection. All right, so if that's the case, then we have a 2 gauge, all right? And that's what we're dealing with. So let's kind of go back to our graphic and kind of work this thing out. So here is 125 rated overcurrent protection to protect the primary. And these conductors were a 2 gauge at 115 amp rating. Now, can I terminate a 115 amp rated conductor on a 125 amp rated overcurrent protected device? And the answer to that is most certainly yes. And you say, well, wait a minute. Am I not protecting it at its ampacity? Well, that's when we're going to go look in the code, and we're going to look at the corresponding device and that is going to be, again, at 240.6a. And we look at it and we say, well, I don't have one for 115 amp rating of that conductor. So I'm allowed to use 240.4, which states if overcurrent device is rated 800 amps or less, and the conductor is not being protected, is not part of a branch circuit supplying one or more receptacles or cord and plug connected portable loads, and the ampacity of the conductor does not correspond, then I can go up to the next size rated overcurrent device, okay? And it doesn't exceed 800 amperes, okay? So we're allowed to do that. And so in this case, we look back at, excuse me, I want to go back down to our table here. It didn't correspond, so that's why we ended up at 125. And yes, based on the rules of 240.4b, we are protecting that conductor at its ampacity. So we're good to go. So in theory, at this point, we're not only protecting the primary of this transformer, but we're also protecting the primary conductors as well with this one device. Okay, so that's how we're doing that. Okay, now we're going to learn how to size the overcurrent protected device on the secondary. But what we're not going to do is we're not going to size the conductors to the secondary. Okay, we're not going to size that. What I will tell you is how to size the conductors before you applied any of the tap rules or the secondary conductor rules. So we're just going to size the conductor based on what we have. And we're going to leave it at that for this video. And then we'll let that carry over into the part 3 where we talk about sizing conductors. And it's going to be a little redundant because we're going to do primary again, but we're also then going to start getting to the different components of the secondary protection. And that's going to be multiple part series as well, because we have tap rules and then we have secondary conductor rules all found under 240.21. Okay, so we got to keep those in line with that. So let's go on now and see back to the table in 450.3b and see what is the maximum size of the secondary protection that's protecting the secondary of that transformer winding. Okay, so we're back to the code. So now we're going to go back to 450.3. So get your code book. Let's go back. Remember in the 2017 NEC. And here we are. All right, so this had a secondary protection of 125% was the maximum. Of course, if it didn't correspond, I could go to the next available size. So let's go on and work that out. So let's come back to me. And let's work this out. So we said that the secondary was 208 amperes. Okay, so we take the 208 amperes. Actually, let's use our calculator right here. 208 amperes times 125%, or times 1.25, whatever you want to do. Times 125%, that equals 260 amperes. Okay, so write that down. So that is 260. Now, does that correspond with a overcurrent protected device? Well, we got to go look at 240.6a to determine that. I'm going to tell you it doesn't, but we need to go look at it. So let's go back to the code. Another thing, the reason that we work through the code is to help you get familiar with navigating it. That's the key to passing an exam, is understanding, repetitious, going back and forth through the code to help you understand what you're working on. So it was 260 is what was our calculation. Well, I see that a standard device is 250, and the next size up would be a 300. Okay, so 300. So that's the choice that we're going to have for our secondary protection. So right here, this device in our graphic, whether it was located right here, or we're utilizing the secondary rules or the tap rules, we're protecting this panel board, whatever our load calculation was. But in this case right here, a 300 amp overcurrent protection is what we would need to protect the actual secondary. Okay? And that's what we would need. All right. Now, as far as these conductors, if I wanted to go right off the bat and say, well, you know what? The first thing is first, and what I'm going to learn in the code is that these secondary conductors got to have rules. And there are rules for sizing that are based on 240.21b. If you're using the feeder tap rule, in other words, you have a feeder and you're tapping multiple transformers to that feeder, then you have a tap rule there because that primary conductor is literally tapping a feeder. And so we have rules in there, and we're going to cover those. Don't worry about it in another episode. And so you have some allowances there for sizing these conductors. Ultimately, at the end of the day, I need to make sure that I've got conductors that can handle the load, but we're doing these tap rules because we don't always have overcurrent protection at the location of the tap. Now, when it comes to the secondary conductors, and we'll look back at the graphic, the secondary conductors are these here in our example. Then since we don't have overcurrent protection here, then we're having it down here, and that's governed by certain rules, and they're going to be secondary 10-foot rules, secondary 25-foot rules, and they tell you how to size these conductors. But just for me and you today, since this is a 300 amp overcurrent device, I want to make sure, and I will remind you of something now. When you're dealing with secondary conductors or tap rules, the next size up rule that we used over here does not work over here. You can't use the next size rule up in 240.4b. So whatever these conductors are, have to be rated to whatever the device is it terminates in. And that's a quick tip for the 10-foot tap rule or the 10-foot secondary rule. Okay, so in our case, let's just go on and finish this one out, and we'll go on to sizing conductors in another episode. But here, what size conductors would we need for this 300 amp overcurrent protected device? Okay, and so this is just the basic rules. So we already covered our foundation of what this episode was about. We've already covered that. I'm giving you some bonus material. We've sized the primary overcurrent protection at 125. We're sizing the secondary of this transformer protection at 300 amperes. But so that we want to size the conductors, let's go on and see what it would be before we applied any type of tap rules or any type of secondary conductor rules. What size conductor would we typically size to go to this termination into this overcurrent device? Okay, and we'll see whether that holds up later on in the other series. Okay, for what we're dealing with. All right, so there we're going to go to the NEC, and we're going to simply got to find a conductor. And we're going to go to 31015B16 again. All other things being considered, 75-degree rated terminals, nothing changed there. We're still using THHN, THWN-2. And so what we're going to do here is find something that's going to handle 300 amperes. Well, it looks to me like we could use a 350 KC mil. And remember, copper unless expressed otherwise. In your exam, always assume copper. Of course, you could do aluminum in the real world, but whatever's on exam, assume copper. Now, why couldn't we use 285? Because we know that there's no breaker that corresponds with this under 240.6a. Well, the reason for that is, again, that we are unable to apply the next size up rule. It says that right there in the charging statement of 240.4. Okay, and it reminds us that we cannot use the next size up rule. All right. So whatever that device is it terminates into, that's what those conductors have to be rated. Now, we are going to see some caveats to that when we're dealing with secondary conductor sizing and when we apply the tap rules, most notably when we're dealing in 240.21B3, which is a 25 primary secondary or primary plus secondary tap rule. And that would be tapping a feeder. Whereas the actual feeder overcurrent device is serving as the primary protection for that transformer's primary. Okay, it gets more complicated, so we'll look at that in another episode. So we've already met our goal. We know what size the overcurrent protection device on the primary is, and we know what it is on the secondary. And arbitrarily, bad word, up front, based on what we know, we're going to size the conductor at this point based on a 350 KC mil. Of course, I could parallel it because 350 is kind of large, and we follow paralleling rules and things like that. But that's what we're going to do here. We're sizing it that way. Now, we're not going to get into sizing the grounded conductor in this episode. We're not going to, because we'll do that when we size the conductors itself. We're not going to size equipment grounded conductors and supply side bonding jumpers here. That's another episode that we're going to talk about all that. So all we did here was tell you how to size the primary and secondary device. 120 primary, 300 secondary. That's all we needed to cover at this point. In our cases here, we determined the size of the conductors, 2 gauge on the primary side, and 350 KC mil on the secondary side. That's before we've done anything about the secondary conductors. That's just based on the loads that we have at hand. And we don't even know anything about the loads that were calculated. We're assumed that those were done, okay, and the transformer was sized accordingly. Okay, we're assumed that was all done. All right. So that's all we're going to cover in this episode. hopefully you got something out of it, because now we know how to take what we did in part 1 and now apply it to find out what our overcurrent protection for the primary windings would be on the primary side based on that transformer primary rated current, and the secondary rated current in order to size our secondary. Okay, and these are maximum values. Now, one last thing I want to cover. When would I use the 250% on the primary? Okay, when would I use that? Well, let's go to our presentation again, and I've got a little slide that wants to deal with that, just to talk about it. Here it is. Now, I'm going to read this to you. This is talking about when you might want to use the 250%. It says 250% rated primary protection has a more common and widely applicable advantage in making it possible to feed 2 or more transformers from the same primary feeder. Okay, so let's come back to me so I can paint your picture. So I have a feeder that's going out, let's say, out and going into a trough or a wireway, and then out of that wireway, I'm tapping using the tap rules under 240.21b3, and we'll cover that in the video. But here I've got these primary conductors that are coming, no overcurrent protection at the tap. It's using that protection back at the feeder, and I'm meeting this rule, and that is your 25-foot primary plus secondary tap rule. Okay, and so we'll cover all about that. But maybe I have multiple transformers here, and I'm dealing it with that way. Okay, so maybe I need the advantage of this 250% so I don't have nuisance tripping, or I don't have an inrush because I have multiple transformers connected to this common feeder. And I want to make sure that I use all the benefits of the 250%. For the real world, when you're dealing with a single transformer like we did today, then you're really going to size it to probably serve double duty because we don't need extra equipment in there. It costs money. Okay, so in our case, we used 125% so that it helps to correspond with what we did with the conductors, so that we know that that one device protects both the primary of the transformer as well as the conductors that are being from primary protection to the transformer. Okay, so we did that together, but let's get back and read the rest of this, because this is a unique situation, and that might be an example where you would use this rule. It says, the number of transformers that might be used in any given case would depend on the amount of continuous load on all transformers. Obviously, we have to do the calculation out and assume that and size that feeder to be able to handle all that. So really, the number of transformers that we could have tapped to that feeder is all based on a calculation. Okay. Now it says, but in all cases, the primary protection, okay, which was back there at the feeder, must be rated not more than 250% of any one of the transformers. And now, if they're all the same size, any one of them. Now, or 250% of the smallest transformer if they are different sizes. Now, what does that mean? Well, if you base it on the largest one, then you're grossly going to exceed the 250% of the smallest transformer. So you always use the smallest one. That way you know that that primary is never going to be exceeded 250%. Okay, so if they're all the same size, you just take one of the transformers and you do it that way. Okay, but in this case, we always, if they're different, then you simply take the smallest transformer when you're applying this 250%. Okay, and we'll finish this one out here. It says, or 250% of the small. Now, if they are all different sizes. Now, and for each transformer fed, there must be a set of fuses or circuit breakers on the secondary side rated at not more than 125% of the rated secondary current. Okay, all right, so what does that mean for us? That's based back on our graphic, and let's go back to our graphic here. So again, let's say that we had a feeder that came out of here, and I had multiple transformers here tapping off of it. And when the secondary comes out of these transformers, then I have to have secondary protection. So that's the 125%. All right. Don't worry. We're going to cover all that if that seemed confusing. I just wanted to kind of cover it. Okay. Because there is an application where that 250% might be utilized. But for me and you, for everyday applications, or except for an exam, you're going to use the 250% because that's an exam question. But in reality, we're probably going to use 125% unless, for example, that can't handle the inrush of the transformers. Then we can go up to 150%. And again, we got to keep an eye on our conductors to make sure they're protected. All right. But there's some rules that we apply to that. Okay, now if I did that and went up to 150 and I had the same size conductors I did at 125, then it might be beneficial for me to start looking at the tap rules that we just talked about for the 240.21b3 because that might benefit you a little bit. And so we're not going to cover that. We'll cover that in that episode, but I don't want to get too complicated with it. So you understand the basics, okay? So we covered all we intended to cover here. The last thing I guess I was remiss, because I want to cover this, is to go back and look at the code when we don't need primary protection, okay? In the type of transformer that we're dealing with. All right, so let's go back to the code. I want to cover that really quickly so that we don't lose sight of what we're dealing with. And we're going to go to 240.21 again, because obviously we're dealing with the overcurrent protection. And here is where the primary can actually protect the secondary. And when can that happen? It says, in single phase other than 2-wire and multi-phase other than delta-delta 3-wire transformers shall not be considered protected by the primary protected device. What does that mean for us? Well, here's what it means. All normal cases with all normal transformers, we're going to have primary and we're going to have secondary protection. However, if we're dealing with a transformer that is a single phase transformer that has a secondary that's only a 2-wire secondary with one single voltage secondary, it means it's only one voltage output. Okay, I shouldn't say output. The secondary side only generating one voltage. Then the primary overcurrent protection theoretically can protect the secondary windings. Okay. Now, what about with a delta to delta 3-wire secondary? Under that rule as well, if I have a delta to delta 3-phase transformer setup and the secondary 3-wire setup of that transformer only has one voltage value, and that would be like a 480 or a 240, and that's the only voltage value on that secondary delta to delta transformer, then that primary overcurrent protection could protect the secondary of that transformer. That's the only rule here when you're not dealing with protection, okay, on the secondary. Now, we're not going to get into applications where power loss and things because generally you also can utilize primary only, and it doesn't have to have overload protection if you're dealing with things like fire pumps or critical systems. We're not going to get into the power loss applications. Just remember primary protection, secondary protection in all cases in transformers, except when we're dealing with a single phase transformer with a 2-wire secondary that has one voltage value, or a delta to delta 3-phase where the secondary is a 3-wire delta with one voltage value. Then the primary can protect the secondary windings in that case. Any other application, we need primary and secondary protection, and that's why in our example we used the values on the second part of the table in 450.3b, because we did have primary and secondary protection. Okay, so hopefully that covers it up for you. There's a lot to learn in that episode. That was a little longer than I wanted it to be, but again, it's an important series to be able to get you on that foundation. If you need to know more about the transformers, go on to the other parts of this series. If you want to learn about conductors derating demystified, go watch those videos on our YouTube channel. Visit our website, masterthenec.com, and you can watch all our videos, our YouTube channels. Share these videos. So that covered what? So part 1, we covered primary and secondary transformer rated current. Here we covered the overcurrent protected devices on the primary and secondary. We also kind of dabbled in the conductor sizes, so that means the next one should be pretty short. So let's move on to the next video in this series. Thanks again. God bless.